Good morning, everyone. Good morning and welcome to the sixth webinar of the Institute of Mathematics webinar series. So I would like to remind everyone that this webinar is being recorded and it is being streamed live on our official Institute of Mathematics Facebook page. Our speaker for today is Mr. J.B. Peñaflor. He will be speaking for the group's Geometry and Representations academic group of the Institute of Mathematics. So today he will present his work titled On the Existence of Triangular Skeletons of Minimal Surfaces in S3. So let us all welcome Mr. J.B. Peñaflor. J.B.?
Hello, good morning. Morning, faculty members, students, guests. Today, I have the privilege of talking about my recent research on minimal surfaces. I will be discussing, based on the title, the existence of minimal surfaces with triangular skeletons in S3. I'm going to start sharing my screen so I can present my slides. Okay. Just like to verify that you guys are able to see my screen.
Yes, we can see your screen.
Okay. So let's begin. We'll actually be covering 4 sections in today's talk. I'll be giving a brief introduction of maybe a history of why I chose this topic, some preliminaries that will assist us in understanding the concepts in the construction of these minimal surfaces. And then we actually construct the surfaces themselves. We'll discuss the construction procedure. And finally, we provide a sketch of how we verify that there is an existence of these surfaces that are minimal. So in 2018, there were 3 Chinese mathematicians, Sheng Bai, Chao Wang, and Chi-Cheng Wang, who actually worked on an earlier work created by H.B. Lawson. In their study, they actually constructed symmetric embedded minimal surfaces in the 3-sphere S3, employing H.B. Lawson's work, the Lawson existence theorem, and the symmetries of the Hopf fibration. They accomplished this using certain quadrilaterals in S3. These quadrilaterals have these characteristics. Each edge of the quadrilateral is also a geodesic, and each internal angle is an integral fraction of pi. So it begs the question, is it possible to simplify, or what is the smallest type of skeleton that will allow us to create a minimal surface on S3? In this today's discussion, we'll actually prove the existence of the minimal surfaces using triangles instead of quadrilaterals. The triangles also have edges that are geodesics, and the internal angles, the 3 internal angles of the triangle, are also an integral fraction of pi. Now we will be using the natural tessellations of the 2-sphere S2. We are tessellating the sphere into triangles, and due to the graphs of its reflection group, so the reason why we are able to create these tessellations is because of the graphs of the 5 reflection groups in S2. And then we will lift these triangles to the 3-sphere S32. And this will allow us to obtain our fundamental triangles. And because I said earlier that H.B. Lawson created laid the foundation for creating the existence, or for verifying the existence of minimal surfaces using conditions that he specified in his theorem, we will be using these conditions to verify that the triangles are skeletons of minimal surfaces using the Lawson existence theorem. So In order to kick things off, we will go through some definitions. In fact, we will be defining the three-sphere of radius 2, and the two-sphere. We define them as follows. So first, we define the set E3, which is the set of all p plus xi plus yj plus zk in the quaternion space H such that t is 0. Clearly, we can see that t plus xi plus yj plus zk is a generalization of the quaternion numbers. It's a general quaternion number. And in this particular space, E3, we notice that this is a subset of a four-dimensional space. In fact, this is a projection of the four-dimensional space onto a three-dimensional space. Next, we define the three-sphere S3. Three-sphere S3 is just the set of all points from the origin with a distance of 1. So this is a four-dimensional analog of the sphere and the circle. S32 is similar to S3. S32 is actually a three-sphere, but this time it has a radius 2. And the reason why we're choosing a radius 2 because it actually simplifies the computations, and it's just really a whole lot simpler if we use the S32 versus S3. And finally, S2 is our two-sphere. It's actually a three-dimensional sphere, and it's the set of all points from the origin with a distance of 1. Now, we call H the quaternion space, where I, J, and K are defined to be the regular quaternions. And the properties of these quaternions are also indicated on the slides. Now, notice also that every point on S3, we can actually think of every point on S3 as a vector or a quaternion. And notice that each of these points on S3 have a norm equal to 1. And that will be very important. Now, let's take 2 of these points on S3 and any point on the quaternion space H. And we define this map from H to H such that small h is mapped into P inverse HQ. Now, geometrically, this actually describes a rotation on H defined by the quaternions or the vectors P and Q. So depending on the values of P and Q, you can actually rotate the H. And we define, or rather we denote this rotation by the notation square bracket P comma Q. Let's look at some properties of this particular rotation. First off, if we get the norm, or we get the length of P inverse HQ, we actually see that the norm is equal to the norm of H. What does that mean? It means that if we subject H to a rotation defined by P and Q, the length of H is kept. And in fact, the orientation of H is also kept. Therefore, we can say that this rotation PQ, or rather square bracket P comma Q, is orientation preserving and is isometric. And therefore, square bracket P comma Q is an element rather of the special orthogonal group SO4. Now, if we take the special case where the rotation is just defined by P, therefore it's just dependent on P, notice that by the same arguments that we presented earlier, this rotation actually preserves the orientation and in particular the length of 1. 1 is very important because you can actually represent everything in terms of 1. So you can represent 2 as 2 times 1. And therefore, what this means is that this particular rotation preserves all of E3, the three-dimensional subset that we talked about earlier. It's also, so it preserves the length, therefore it's isometric. It also preserves the orientation. Therefore, this rotation square bracket P comma P, which we will be denoting by square bracket P, is in itself a special type of rotation. It's in fact a rotation that is an element of SO3. All right, so now that we have discussed those preliminaries, we'll be needing those for our notations later in certain theorems and in certain lemmas. Now, let's take two members of S3. Oh, sorry. Now, let's actually define what a geodesic is. So earlier, I talked about the geodesic. In fact, when I presented the idea earlier, I talked about the sides of the triangle, the fundamental triangles are geodesics. So let's define mathematically what a geodesic is. I took this definition from the standard textbook in differential geometry. So we define a curve C on a surface capital M as a geodesic if its tangent vector is parallel along the curve. So that means that the directional derivative of the tangent vector along the tangent vector is identically zero. So visually and geometrically, we can also think of the geodesic as the shortest distance between 2 points on the surface. Recall that the surface, based on geometry, is not necessarily flat. I mean, on a flat surface, the shortest distance between 2 points is a line, and that in itself is a generalization of a geodesic. But let's say on the sphere, if we consider 2 points on the sphere, or let's consider 2 points on the surface of the planet Earth, then the shortest path between those 2 points is actually a path along a great circle. It's actually a minor arc along a great circle passing through those 2 points. And now we will also be discussing the enlarged Hopf fibration. The Hopf fibration is actually discussed or defined in the lemma. This allows us to construct geodesic triangles that are closed. It's important that the geodesic triangles are closed, and that these triangles on S2 need to come from the point I, and then they will be lifted to triangles in S32 that contain the point 2. Let's look at the lemma. Oh, okay, before that, we are using the S32 sphere, as mentioned earlier, to simplify the results. This is the lemma. It's called lemma 2.4 in the research, and we define the math-calp. Math-calp characterizes the enlarged Hopf fibration. Math-calp is a map from S32 to S2 such that a point R in S32 is mapped into R inverse IR. Let's examine what happens. And these three conditions that follow are actually, the 3 items that follow, conclusions that follow, will be important in our lifting and in our discussion. First off, every fiber in that fibration is of this form, e to the I theta over 2r, where theta is a real number. And with r, as mentioned earlier, in S32. And it has a length 4 pi. It's very clear because every fiber in a Hopf fibration is a circle. And because the fibration is on S32, which has a radius 2, then that circle has a length 4 pi. Next, given any r in S32, our 3-sphere radius 2, and let's say we have a piecewise geodesic, that means that we have a geodesic that's connected end to end. And this geodesic exists in S2. We can actually uniquely lift that. And the point is uniquely to a geodesic in S32, which we denote as tilde L of S, with the following properties. Number 1, the lifted geodesic tilde LOS intersects the fibers orthogonally. And number two, the lifted geodesic is locally isometric to L of S. That means that the length of the segments in the geodesic, in the lifted geodesic, are the same as the lengths of the segments in the original geodesic in S2. And then the angles between these geodesic segments also have the same measures. And then finally, what if we actually close the geodesic or the original geodesic in S2? We can uniquely lift that to a closed geodesic in S32. So if, let's say, and as mentioned here in part C, if L of S is instead a closed geodesic triangle in a closed hemisphere of S2, it means that it does not exceed one hemisphere, then the lifted graph, which is L of S, is in itself a closed geodesic triangle. So using lemma 2.4, we shall actually be creating our minimal surfaces. Lemma 2.4 gives us the construction procedure. But where do we get the original triangles from? Lemma 2.4 requires that we have some triangles to begin with to lift the triangles in S32. Fortunately, we actually can look at the tessellations of the two-sphere. We can look at the 5 finite subgroups of the isometric group of S2 generated by reflections. These 5 groups are called C, D, T, O, and I. And they're named as such because C is a cyclic subgroup, D is a dihedral subgroup, T is named after the symmetries of the tetrahedron, O after the symmetries of the octahedron, and I on the symmetries of the icosahedron. Now, I'd like you to look at these groups and notice that these groups have rotations as the generators of these reflection groups. For instance, if you look at D, notice that all 3 members or all 3 generators of this group are in SO3. That means that they're orientation preserving and isometric. And I mentioned D because we're particularly interested in the dihedral reflection group D. When we look at D, it actually tessellates the sphere. And you know, the lines that tessellate the sphere actually defines a graph. And the graph, and because of the graph, we're able to actually tessellate S2. And each typical piece of the two-sphere S2, we can call triangle D. And the reason why I'm choosing D is because this is the simplest to work with. The others, you'll actually have a little bit more challenge to look at the reflection groups of T, O, and I. And D is really relatively easy. And it's also easy to draw. Let's look at the typical piece triangle D. This is how the typical piece looks like. So coming from I, and then we have this point K. And then we have this point, which is e to the negative pi over L of a distance from K, and it goes back to I. This typical piece has angles pi over L. Pi over L is this vertex angle over here at I. And then we have 2 right angles. The area of this triangle by the spherical excess theorem is actually pi over L. Now, armed with lemma 2.4, when a graph denoted by capital gamma of D is lifted to S32, that means that, let's just say that gamma sub D, and you have, let's say, a path over here, and a path over here, and a path over here. So the graph the set of all graphs, right? When lifted to S32, actually defines, we can actually define two types of graphs. These two types of graphs are denoted as tilde gamma d of L, which is just dependent on L. And it generates a group called G of D, G sub D of L rather, having an order of 8L and generated by these three reflections. Notice that these three reflections are actually in SO4. All three reflections are elements of SO4. The second lifted graph is dependent on both the length and pi over 2. And it generates the group G of D having an order for L squared. The generators are indicated here. I'm not going to show it here, but we can actually see that even if they have two different graphs, right? When you lift gamma sub D from S2 to S3 and result to gamma tilde of L or gamma tilde of L and pi over 2. They may create different graphs, but both should actually yield the same triangle. So if we're just going to look at the triangles, these two different graphs, lifted graphs, should actually be the same. All right. So now let's move on to the construction procedure. We will call a triangle in S32 as a fundamental triangle. It will be the basis of our triangular skeleton. And our fundamental triangle ABC, we'll be calling it triangle ABC, is lifted from triangle D in S32. We do it as follows. So starting from the point I, we go down to K. So this is a geodesic that's connecting I and K. And since this geodesic in S2 passes through the point I, then we can uniquely lift this to another geodesic that goes through the point 2 in S32. Second, coming from K, we move to e to the negative pi over L times K, which is just essentially e to the negative pi over, or a distance of pi over L rather from K. And then because of lemma 2.4, we can actually lift this uniquely to another geodesic in S32. Finally, from this point, we go back to I. And because it goes back to I, this can be uniquely lifted again to another geodesic in S32 going through the point 2. So now, by the power of lemma 2.4, we know for a fact that the lifted triangle ABC will be simple and closed. In order for us to see the properties of ABC and the side and angle relationships, I've actually colored the sides of ABC to correspond to the geodesics that compose our triangle D in in S2 rather. So this is the triangle D in S2, and this triangle ABC is in S32. By virtue of the lemma 2.4, since we are using the Hopf vibration from S32 to S2, we know for a fact that the side and angle relations in triangle D are the same as the side and angle relationships in S32. Now, one thing that sticks out is this. What is the biggest possible value of L? Biggest possible value of L is 1 because L is a natural number. And therefore, the biggest size of angle A is just pi. And therefore, this triangle ABC can fit within a hemisphere. And that fact is very important as we go through the second lemma, which we will be calling lemma 3.5. The lemma 3.5 allows us to actually say that the triangle that we have defined earlier is actually a there's an embedded minimal disk that is equal to that triangle, and this will be important when we go through the conditions of the laws on existence theorem. So we define mathcal H as the set of all closed hemispheres in S32, and we define mathcal C of T sub D rather, to be the convex hull of T sub D, defined as the regular definition of a convex hull. Then the convex hull itself is a geodesic triangle in an open hemisphere of S32, and the elements of the orbit of the convex hull only meet at their boundaries. And furthermore, as mentioned earlier, there exists an embedded minimal disk D such that the intersection of D with the boundary of the convex hull is the boundary of the disk itself is equal to the triangle itself. Let's look at the sketch of the proof. First, let's look at part A. So T sub D is a triangle. It has interior angles and side lengths no greater than pi. In fact, triangle ABC is a special case of T of D. T of D is a generalization of this concept. By construction, any two vertices of the fundamental triangle are never going to lie on the same geodesic, because we also constructed the triangular or fundamental triangle to be the lifted graph of a closed geodesic triangle in S2. Therefore, if we examine the convex hull of these 3 points, the convex hull is a spherical triangle in S32, defined exactly by these 3 points. And since no side or no angle is greater than pi, the triangles will always be contained in some hemisphere of S32. Secondly, let triangle ABC be in the orbit of T sub D. So let's consider one particular triangle in the orbit of T sub D, triangle ABC. Remember, triangle ABC is in S32. Consider now a pi rotation around the side AB. So essentially, you're just really, let's say you have a triangle, and then you're just really reflecting it along the side AB. And because of that, you're able to map this pi rotation actually allows you to map the original triangle to another triangle, triangle ABC prime. Let's look at what happens in S2. In S2, because of the enlarged Hopf vibration, mathcal P of the side AB actually maps the triangle or the image in the Hopf vibration, which is a triangle, to another triangle. So essentially, in order to obtain the triangle ABC prime, which is in S32, we are just really lifting this triangle S2, triangle in S2 from A. Generalizing this for all such triangles, the orbit of T sub D is obtained by lifting the orbit of P of TD. And therefore, assuring us that the orbit of the convex hull only meet at their boundaries. This allows us to confidently say that we can definitely find the disk D in the convex hull such that the boundary is the triangle itself. So well and good, we have shown so far that we can construct just by the tessellations of the triangles in the two sphere. We lift these tessellated triangles in S32, and we can actually form a surface out of it. Now, we need to show that the surface resulting is actually minimal. But before we prove the main result, which we will be proving using Lawson's existence theorem, we state a few definitions. This time when you see capital gamma, it's a general polygon. Okay, let's denote capital gamma in S32 as a generic geodesic S+1 sided polygon having S+1 vertices and S+1 sides. We represent the vertices by subscripted V's, and we represent the sides by subscripted small gammas. For any two geodesics that meet in S32, we denote by S of small gamma and delta. Say we have two geodesics gamma, and small delta. The unique geodesic two-sphere in S32, which contains both gamma and delta. And finally, we let N sub T be the geodesic perpendicular containing both sides, any two consecutive sides at their common vertex. We define a bounded subset as a subset of S32 bounded by S of gamma and delta if the subset is contained in either one of the two closed hemispheres defined by S of gamma and delta. We next define a proper polygon. A proper polygon is a polygon such that if for every side, there's a unique geodesic two-sphere that bounds both the side and the geodesic perpendicular. And then another important definition is a polygon that is convex. A convex polygon is defined as follows. First, let's define mathcal H to be the set of all closed hemispheres in S32. And let's see mathcal C of gamma be the convex hull of gamma defined as follows. So we saw this definition, or we saw this first part in the previous lemma earlier. If gamma or the polygon is a subset of the boundary of the convex hull, then gamma itself is a convex polygon. Now, let's just look at this. We easily see that triangle ABC, or one of our general triangles, is proper because there's always a geodesic two-sphere that bounds a side. This is the geodesic two-sphere. And a geodesic perpendicular to the side. It's also convex because the convex hull of the 3 points is the entire triangle itself, and it defines the boundary of the convex hull. Okay, so let S sub gamma, this time this is a scripted S, be the set of geodesic two spheres in S32 such that we have a two-sphere S, which is an element of scripted or mathcal S of sub gamma. If and only if the intersection of the two-sphere with gamma has at least three components, as in this case, right? So these 3 points are on the surface of this two-sphere, and clearly there are three components. The three components are these 3 points. And lastly, we denote by the symbol the interior of the convex hull, and we denote by D bar the closed unit disk. We are now ready to define, or we are now ready to state rather, Lawson's existence theorem. Let's read Lawson's existence theorem. For a proper convex geodesic polygon gamma in S32 having vertex angles of an integral fraction of pi, where L is a positive integer depending on the vertex, means that the vertices, all the vertices will have a fractional vertex angle. Let G of gamma, G sub gamma, be the group generated by pi rotations around the edges of gamma. If capital gamma satisfies the conditions A to D, which we shall see later, then there exists an embedded minimal disk, mathcal M sub gamma, which is an element of the convex hull of gamma, such that mathcal M sub gamma intersection with the boundary of the convex hull is equal to the boundary of the minimal disk M sub gamma is equal to the polygon itself, gamma. So this form is very similar to lemma 3.5 that we saw earlier. Moreover, let M sub gamma be the union of the orbits of mathcal M sub gamma under the action of G sub gamma. Then M sub gamma is a complete non-singular minimal surface in S32, and it is compact if and only if G of gamma is finite. So actually, we already have the elements needed for this particular theorem. Our G sub gamma is the group generated by the graphs of gamma sub D in S32. Our minimal disk M will actually be our triangle ABC, a fact that we have actually proven in a previous lemma. Now we just really need to look at 4 other conditions. What are these conditions? Number 1, gamma, or the polygon, lies in an open hemisphere of S32. Second, for each point in the interior of the convex hull, there's a geodesic two-sphere, SP, that's not in a mathcal S sub gamma containing the point P. For each T, that means that for each vertex, if you have 2 successive, this is, let's say, the previous side, and this is the next side, and the common perpendicular end of T, and it fails to bound gamma, then L of T equals 1. And finally, there exists a continuous map rho from the convex hull to the unit disk D, which is differentiable in the interior of the convex hull and carries gamma monotonically onto the boundary of the unit disk D, such that for every S in mathcal S sub gamma, the differential of this map is everywhere of rank 2. We will be going through the verification of these conditions in a sketch. The definition, or sorry, these 4 different conditions rather are proven in the paper. To prove condition A, we have actually mentioned this earlier. Triangle ABC is in an open hemisphere of S32. We saw that no sides and no angles are greater than pi. Clearly, triangle ABC satisfies condition A. Second, triangle ABC satisfies condition B, and this is coming from the fact that it is a proper polygon. Much time is actually spent in the paper to prove that triangle ABC is a proper polygon, and therefore there's a two-sphere containing every point in the interior of the convex hull of triangle ABC. Third, we can always find a two-sphere that bounds 2 adjacent sides of triangle ABC and the perpendicular at the common vertex. And this allows us to satisfy condition C. The fourth condition is actually a lengthy one to prove. And we do it this way. We actually define D plus to be the 2-dimensional open hemisphere, this time centered at the point 2. The point 2, as we recall, is in S32. And this open hemisphere rather, is orthogonal to the fiber at P inverse I. Remember that P inverse I is also in S32. So the fiber P inverse I is in S32. Then we can actually show that there exists a map rho. We show this by construction in the paper. From the convex hull of triangle ABC to the closed unit disk D plus. So our closed unit disk D plus is actually the unit disk D bar that we saw earlier. Now, since the dimension of D plus is 2, the rank of rho is also 2. And therefore, by Lawson's existence theorem, we can say that there exists an embedded closed non-singular minimal surface corresponding to our fundamental triangle, triangle ABC. Thus, we have shown the existence of minimal surfaces with triangle skeletons in S3. Again, the procedure is just for the reflection group or using the reflection group D. And that ends my presentation for this morning.
Thank you very much, Mr. Peñaflor. Let us, everyone, let us all give Mr. Peñaflor a round of virtual applause. Okay, so thank you for that nice talk. So the floor is now open for any question. So you can unmute yourself if you have questions on the talk. Yes, we have a raised hand, Mr. Ventura.
Good morning.
Good
First of all,
morning.
thank you for the talk. I would just like to ask if there are any thematic differences between what was done in I believe 2018 using geodesic quadrilaterals and what you did in the paper using triangles.
Thank you so much, Jade, for that question. In terms of the procedures are very similar, right? Because we're actually referring to the same reflection groups. We're starting with the same reflection groups. We're starting with the same tessellations in S2. But the difference actually lies when we already lift these triangles to S32. Remember in the original paper for in 2018, these triangles are lifted, but as they are lifted, the original researchers create quadrilaterals coming from the lifted graphs instead of just focusing on the triangles. Then that's in itself a different theme. For one, in the original paper, their convex hull is not a triangle. Their convex hull is a tetrahedron. Of course, it's a, shall we say, spherical tetrahedron, if you know what I'm saying, from four-dimensional space. So, and then they have a different way of showing the perpendiculars. Remember earlier I talked about the common perpendiculars between two consecutive sides. There's a different way of showing that in their theorem, or rather in their paper, using quadrilaterals, simply because the convex hull of a quadrilateral is a tetrahedron, or 4 points is a tetrahedron. So those are thematic differences, plus the fact that they actually characterized the minimal surfaces that resulted from lifting those triangles from S2 to fundamental quadrilaterals in S32. I hope I answered your question, but feel free to provide a follow-up question if you have.
No. Thank you very much for providing the answer. Thank you.
Okay, thank you, Jade, for your question. Do we have any other question from the panel, from the audience? Yes, Mr. Peñaflor, you mentioned that, so you are referring to a paper. So is this paper published, or is it on archive, so that if there are people who wish to look at it and refer to it?
Yes. Thank you, Sir Gino. Yes, it is published. They can actually find the paper. It's you just really need to type the names
So
of.
they can search the title.
They can search for the title. Yes.
Okay, and Mr. Peñaflor. Okay. Okay, are there other questions? Okay, if there's if there are no more questions, let us once again give Mr. Peñaflor a round of virtual applause. Thank you, JB, for giving that nice talk, and thank you to the audience. Now, so in 2 weeks we'll have our final webinar for this semester, where we'll be hearing from the optimization and approximation group and the mathematical finance and actuarial science group. Okay, so until then, May 31, I will, so this is goodbye, and then I will see you then. Okay, goodbye.
Thank you,
Thank you
sir.
again, JB. Thank you.
Thank you, JB.